of the workshop, we have Mr. Johannes again now deliver a hands-on session on multiphase and multiphase. Phase change open form.
Welcome back and welcome to a small hands-on. I hope it'll work and we'll see something. But first I will show a few peculiarities which you encounter for these type of simulations, and then I will go into. If you do multiphase phase change simulation, you get additional time step criteria which are tighter than which get even tighter than in single phase or simpler problems. You need to initialize the volume fraction field. You have to think about where is the new bubble. A bit on the selection of solvers, then a small life on how to deal with intensive modeling. So, if you've ever performed a simulation, CFD, you will have encountered the Courant number or Courant-Friedrichs-Levy number, and you are usually told set it to 1. And it's defined by the length which is traveled by the cell size. And in multiphase, it is usually recommended to go slightly slower. Example values like 0.2, which sounds like a small difference between 1 and 0.2, but you drive up your simulation times by 5. You have to repeat 5 times. Then there is a criterion which is based on the resolution of capillary waves along the interface. And for multi-region, we get, well, we actually also have single region cases. We have to keep track of diffusion processes, and especially in the solid. So how much distance is the thermal diffusion traveling compared? And unfortunately, although the phase change source terms are actually explicit, there are no criteria, no time step criteria for it. And this is one of the reasons why these kind of simulations have a delicate handling. If you analyze the dependencies, for the Courant number, you have just linear relation with the cell size. Here you have the power of 3 by 2, and here you have squared. And this is one of the reasons why it's very costly to define your mesh, because these time step criteria will hurt. And from experience, in Darmstadt, I have excellent computing possibilities. We have a high performance cluster. I have lots of power available. And the problem with going to very small time steps is not that the solver couldn't solve the huge equation system on time. It is just that it has to be repeated 10 times more or something like that. On to the initialization of the volume fraction. There is only one method known to me, multiphase method, which can really or approximately model nucleation, and that is the Lattice-Boltzmann method. Don't ask me how, it's not my field of expertise, but research it further if you're interested. All other methods, multiphase methods, we have to give a nucleus or initialize somewhere. And for example, in my cases, close to the space experiment, I have a preheating of a single phase fluid on the heated solid, and then when the bubble growth starts, I have to manually set the volume fraction value in the region so that they form a vapor bubble. In my case, that is quite tricky because if you just set a circle somewhere at the wall, and you happen to initialize a bubble with a greater contact angle than the prescribed contact angle, this force from the contact angle modeling pushes the contact line inwards, and in microgravity, this often leads to detachment, like the process from the sound coiling, what do you call it again, the pinching, bottom, similar phenomenon is happening. But you can do geometric considerations to find out exactly at which height you should initialize the vapor bubble so that it doesn't detach right. You've seen this text, I just repeated. We have no official solvers. I've just heard that Fluent is capable of doing similar things right now, but it's all rather basic, and therefore I am using this two-phase flow library also for the hand. Now it becomes slightly technical. Where to set these models I've selected in the previous talk. So the multi-phase modeling is really a big part of the modeling overall. So it's really its own solver, and therefore it is specified in the OpenFOAM file for solver. And if you might remember, click RDF for reconstruction and ISO infection for infection. Multi-region, beside the solution of the conservation equation in solid, is then set by a boundary condition at the edge where both regions meet. And phase change is a special model, not as big as multiphase, but also very important, therefore it has its own settings file, and in this file, maybe you can read it, use this. It's in this solver, it's called Schrager, it's this Hertzknutzen-Schrager model, together with this steering of the mass source terms for and then a small life hack for open foamers and all others. I'm sorry if I bore you. Sit back and relax, because from now on it's getting technical. It's often the case that, for example, the saturation temperature, you need to set it in this phase change properties. You might want to initialize fields based on it. Maybe even the contact angle has it. So it's flying around at several locations, and it's sometimes hard to keep track of where do I have to set it. And additionally, and this is true to all CFD, there are lots of settings, and maybe for your development or testing, only some of them are important. And there is a nice solution, because it's all based on C++. You can create, for example, in your top level of a case, an auxiliary file where you store these important values, for example, saturation temperature, and maybe for decomposition, how many cores do you want? And then in these solver files, you include this file. And for me, it's a nice way of not forgetting crucial settings. Again, everyone who doesn't want OpenFOAM, please sit back and relax. Because some will have no experience, some people like Arvind have more experience. I hope I somehow aim at some of you. And for this, it would be magnificent if you know how to use this black terminal, which I'm going to open right now in a few seconds, and compile OpenFOAM, and have a little bit of general coding knowledge, a little bit of C++ knowledge, because OpenFOAM, in my experience, it's equally important to have C++ knowledge and OpenFOAM OpenFOAM knowledge, the way how OpenFOAM is coded, because they have their own classes somewhere. And if you don't understand this structure, all C++ knowledge is worth nothing. It goes hand in hand. And please interrupt me at any moment if something is unclear. OpenFOAM in a now 4 years old version, this additional two-phase flow library, and then I will just use a simple text editor and this bash terminal. What I heard and what I encountered myself are these typical challenges which you have when you develop models or solvers in general and in OpenFOAM. The first one is you should never mess around in the official OpenFOAM source files. Don't change them. But you want to create your own libraries and maybe own solvers which dock on OpenFOAM and do not change the code. So this is the first requirement. And for example, this new temperature boundary condition for conjugate heat transfer which I developed is something like that. It's a module which can dock onto OpenFOAM. The second challenge is also based on this example. Yeah, I said we have to modify the virtual heat transfer coefficient with the volume. And the volume fraction is a solution variable from OpenFOAM, and somehow we have to read it in from the solver. So this is a challenge. And then a very important one, you compile the solver, yeah, from C++ to an executable object. And it's bad practice to change something in the code, compile, change something in the code, compile, test, but you rather want to do tests with runtime selectable variables. For example, if I want to test the influence of setting the limit this alpha here, I want to specify in the OpenFOAM case the value and not go to the source code and change it. And I try to show these three challenges in the following hand. Don't remember this aim. It's purely nonsense, but I hope to show something with it. Yeah? So you might remember accommodation coefficient, and by hard thinking, we speculate that it's a function of the sign of the liquid temperature, somehow the cell center with a factor, and then time multiplied with a constant which we want to modify. And then it would go in the phase change mode. Yeah? So the fictional aim is let's implement equation 3 into our own solver or phase change mode. We need to know where is the solver, where is the phase change code. Then never develop something without a test case. The best case for a test case is an analytical test case, because then you can be sure it's totally correct. Or something where you know what should be happening and you can compare. We have to create a custom repository for our custom code, and then we will do the magic with the accommodation coefficient. If you've ever looked at OpenFOAM, I don't know, have a first directory structure of the source code, and the solver is usually under applications. In our case, it's directly under solver, and you see that in this two-phase flow library, we have 3 solvers, and we are going to use a modified version of this last one because it's multi-region, phase change, and multi-phase. And as previously said, phase change is more a model, and the models are collected under the source folder. either look around, try to find it, or what I find useful is using the grep term in Bash, and then sitting on the top level and looking where is phase change mentioned, and then I get an idea which might be important. We see in this test case, this is the bubble growth case on a heated wall, and I now want to somehow modify the accommodation coefficient in this region. And now I will start with the on the right hand side, this is the terminal. Can I just see a hand who's ever seen it, worked with it? Okay, thanks. At least someone. And I have two tabs open. The first one is the folder where all custom open foam code is located. So this is a library of myself. This is two-phase flow. This is the backup folder. If I screw up, I will use this one to go. And in the second tab, this is where I have the cases which I will run in a second. And I will now follow the instruction on the left-hand side. Is it visible? Can you read the text? It's okay. So in the folder where I have my custom open form code, I will create a folder and put a custom behind it, but empty folder until now. Now, every time you create significant code, you should git it. I hope you've heard of it. This is the version control system. It tracks the changes you have made. And if I were on my own and had more time, I would definitely git it. But for time reasons, I don't do it wrong. Okay, so now important message. I think no one, maybe besides the official OpenFOAM developer, can write a model from scratch. Or it's nonsense because you need 2 weeks. So always look for a similar model, copy it, and then work on it. Yeah? So I will copy from the official two-phase flow library. I copy phase change models into my custom folder which I have just created. Now I enter this folder, and there is this source which only contains the phase change modeling. But if we look into this folder now, we see lots of other code which we don't need right now. We only need the make files. These are important for the compilation, and the phase change models. So I will delete everything else. Now only make and phase change models. And if I enter phase change models, again, there's the mass source term model. We don't want to change it. We only change the energy source term model. So I delete everything except this one. Only energy source term model. And again, there's this gradient-based model. But we only want to work on the shrouding. So I delete everything else. Okay, now we have cleaned up the custom folder, and it's possible that we leave this name Frage, but it's not good practice. We should give it a more sensible name. I've learned from a workshop a variable name is not, or a good variable name is not identified by the length of characters, but by the time you need to understand what it does. So we use a meaningful name. I hope it's meaningful what I choose now. Frage with custom F. And I hope everyone knows. But inside this folder, the files are still have still the old name, so I will also rename. And I now have a new name for the header and the source file. And last step of the renaming, I go inside these files. And this is really simple. Replace all occurrences of the Frage name with our new name. Replace all. And again. Okay, so it's renamed. We go up again where these make files are, and we now have to update these files. So what I explain does only make sense if you've ever seen it, but I will do anyway. Here is the linking of the code against other open foam parts, so that the compilation knows, I need this model and this model and this model. And in the file, you see all. This is from the original one, yeah. The compilation gets told, compile all these files and put it into a library called phase change. What I will do now, delete everything again except our custom Frage model. And now I choose a new name of this library, so that I don't overwrite the original one. Never change original library. Change custom. If I compile now with this cryptic command, I will get an error. Luckily, I expected this one. And the reason is that in the directories which are searched for the other code, they are hard coded with this dot dot, means go up one directory in the Linux world. But we are in our own directory now, so it's better to make these paths absolute. Like this. There's the next one. There's one. And then additionally, we have to let our custom library know where is the original phase change stuff from two-phase. Double. Okay, let's try again. I'm very relieved. So, but what have we achieved now? Nothing. We have just moved the official code to a new library, renamed it, and nothing new. But as I said, this is the first challenge. Never touch official code, but move it somewhere else. Okay, the second step is a recommendation. If you develop something, always try to get to a visible working setting. Yeah? If you want to analyze numbers, we are not made for a long list of numbers. They're much better to spot anything faulty in a colorful image. Yeah? And that's why it's advisable to create a field for this accommodation coefficient, which we are going to modify, so that we can look at it and see, does it do what we want or not. We would do this in the create fields of the solver, and would move or would create our custom solver. I did this in advance. It's really not hard. It's the same procedure as right now. Moving the official solver, renaming, and putting this piece of code in a location where the fields are clear. Now that we have a new library and a new solver, we will have to modify in the case, so in the distribution, different names. So again, this will be cryptic for anyone who's never worked with OpenFOAM. Here you see this life hack where I include some variables. I have renamed the official solver question at the end. And then in the libs section, we have to tell, hey, OpenFOAM, please use my custom library. And we have named this custom library custom. Therefore, the solver now knows where to look for the phase change model. And the settings for the phase change model, again, somewhere in a cryptic place. Here's the original Schrage one, and we have created Schrage with custom F, and this reads from these coefficients. This is the accommodation coefficient, this is gas constant, and as I said in the beginning, we want to use another value in here, which we can change on the fly without compiling the complete code. And in a minute, I will name this variable C, and I will put in an arbitrary value of 1. Let's see if it runs. Does. This is solving. But again, we have done nothing custom so far. It's just showing that moving to our own library is working. Now to the actual modification of the phase change model. We want to implement this equation, and therefore we need to read in this C, which I have just specified. I'm in the header file, and in the header file, the private member variables of a class are defined. Yeah? And we see the accommodation coefficient and the gas constant, and I will add my own scalar to it. in C++, it's common to put an underscore behind a variable if you use it for internal use class. And now in the source file, I have to read in this C from the dictionary interface. So again, see what I did. I did not try to put it from scratch, but I found a similar bit of code. I changed it, and now the solver or the phase change model looks for a C. Is there a C? And if not, it sets this value to 1. Okay, then the next challenge was how to read solution data. Again, everyone who knows this source code here, it's not everything needed, but I only stay in this first function here. There is actually already the liquid temperature, but it's in a custom form of the solver, and I will show you a more general way of getting a field. It's a constant field because we don't want to change it, and it makes life easier for the solver and memory storage if we tell we don't have to change it. Then this is OpenFOAM class. All scalar field, volume field for a scalar, and with ampersand behind the reference to the original field, so that we don't create a new variable, but we just read it. And I now have to ask OpenFOAM, give me the liquid temperature, please. Again, what's happening next is either you know it because you've seen it or not. Now you have seen it, so you use the mesh object, and on this mesh object, we ask for a volume scalar field, the name T.liquid. This is how the liquid temperature is named in solver. And for this function, we also need time. Again, we ask the mesh object to give us time, and then just give us the number. Don't have to put the unit seconds behind.
Johannes, you have to probably name the volume scalar field. TF.
Oh yeah. Yeah. And finally, in this crazy equation, also the cell center x direction is present. So I ask the mesh to give me all cell centers. This is now a vector. I only want to have the x direction first entry. Okay, so I've loaded liquid temperature, time, and location. And now, in contrast to these fields, the field for the accommodation coefficient, this is a field I want to modify. And therefore, I load I first load the pointer to this field, which really points into the memory. And then I dereference this pointer to give me writable access to the field. So this is C++ notation. The star, the pointer, ampersand, dereferences it. You have to see it, and then you know what you have to do. Okay, and finally, this is now relatively nice. We can type the equation very similar to how we would do it on paper. This is an advantage or a strength of OpenFOAM. So TL plus some factor times x minus c. Just for LaTeX. Times c. So we have the function in this code. Let's see if it compiles. Does. And now, test case. Let's see what happens. Oh. Again, some crazy error. Usually OpenFOAM only, or what you usually get is this kind of error. You don't know what it is. Simple exit, operator plus, okay, and you know where it is maybe, yeah. But in this case, OpenFOAM is very nice to us. And if you look up here, it says that we somehow married two quantities which have different units. So, and this is interesting because the compilation worked. We thought we're done, but the whole solution process says, wait a second, your dimensions are not correct, and it even tells us the fourth location. So somewhere we have a temperature plus a length. Of course, this is in the equation here, temperature plus length. And the workaround is, this is a hacky workaround now, there are for sure better ways, but still the equation from the beginning is totally wrong in dimensions anyway. Yeah? So this is a workaround to fix this problem here. In practice, you would never come up with such an unphysical equation. So I will remove the dimensions from the temperature by dividing by the dimension of temperature. I will remove the dimensions from the length by dividing by a dimension of length. And then for time, I did with this value here, I only took the number and not the dimension with it, so I don't need it here. Let's try again. Now I have to compile again. And of course, for this whole modification to be effective, I have to replace the original accommodation coefficient in the code with my modified field. Yeah? So here I replace it. Then okay, and let's hope that this case now is successful. Looking good. Yeah, something is happening. It's not crashing or stopping. And I will have a look at the result. So this is ParaView. This is the software used for visualizing the data. I can look at all solution data. Here the temperatures. Here is the volume fraction. And here is our modified accommodation coefficient. And you see some fun, some dependence on the x, but with a sign. And here in the bottom, where we have a higher liquid temperature, also have a dependence. So it did what we wanted, and what we wanted was total nonsense, but I hope you learned something. Okay, to finish the presentation, for reference, we have created a sign of our accommodation coefficient. What is the result for bubble growth? Of course, total failure. Bubble gets disrupted, nothing works. And if you look in the source, in the solver output now, this is one of the harder error messages. You really have to look what's up. Maybe you see before, right on the top, that the maximum velocity is 5.5 meters per second. We get an idea. And with this, welcome to the daily reality of the developer in the multi-phase, multi-region phase change world. Because this is 90% what happens first, and then you become better. Get better model. Okay, I've shown some peculiarities for this kind of simulation, how to work with code, and we've seen that OpenFOAM can help, sometimes later than earlier, but still be resilient and still have fun with OpenFOAM. Sorry for boring some of you, and thanks for listening.
Are there any questions?
We are working with this two phase flow library. You are showing the ESI version. Whether it will work on foundation version as well?
Is it in the foundation version?
Yeah, this
No,
will come. It is using the original solvers from the not solvers but some tools from the ESI version specifically.
It is ESI, yeah.
Well,
And what are the presentation you made earlier regarding your own repository? Whether that is taking dependency from the two-phase flow library itself?
It is, yeah. But the method itself is universal. So as soon as you have a volume fraction formula,
and one more question I am having is you mentioned about the bubble initiation.
Yeah.
So how you determine the size that you will specify at the T0?
Yeah. So the initial size of the bubble.
Yeah, initial size.
I mean, in boiling, you should choose it as small as possible. This geometric off from the first talk is excellent. You can just in one cell, you can give a little bit of vapor, and it will create you a perfect vapor bubble in 3D. As soon as you are at the wall, as most of us do, no chance. And I did some study on how to choose this radius with a contact angle of 15 degrees, so it's limited universal statement. But I found out you need around 10 times the cell size in radius for the bubble to be stable at a wall.
So that is a function of mesh size you are using, or the fluid property, or both?
Mesh size, yeah.
Mesh size only.
The smaller the mesh, the smaller I can make this radius, but then times that criteria.
Thank you.
so I have a fundamental question. You talked about the CFL criteria.
Yeah.
So if I have a static bubble and I just want to look at its deformation, maybe under the effect of some electric field or something like that. So is it correct to use the CFL criteria for this? Because as is, there is no bulk velocities here. So should I strictly satisfy the CFL criteria, or how does it numerically become stable in this case?
I would say it's if you have a
If it is pure diffusion, you use the diffusivity, or if it is pure advection, if you have a bulk velocity, you use the u delta t upon delta x, but
Yep.
you do not have a bulk velocity and just a small deformation.
yeah, there are two answers. First, if you don't have large velocities go on, or this time step criterion will go to larger
Yeah.
time steps anyway. And then you are totally right. All these criteria are only fully valid for explicit time discretization. In OpenFOAM, we do it at implicit time discretization. So it's less a strict limit, but a recommendation. I have experience. I can sometimes choose much larger values, sometimes not.
Yeah, in theory, implicit is unconditionally stable, but we never do that risk of just taking a very large CFL number, by the way.
Yeah. Maybe because of the phase change. And surface tension model.
Because you also use the capillary wave criteria. Maybe is that the more correct way of using it for just a bubble deformation kind of?
Yeah, this criterion is also interesting. My experience, not so much a stability criterion, but I understand it as: do you want to see the capillary waves?
Yeah.
Or not?
Physical.
Yeah.
Time step. So if there are no further questions, we'll once again thanks to Johannes for